15.1, basic concepts of graph theory. A graph is a collection of vertices and edges. So you can kind of see a couple of different graphs on here. These graphs right here, these things, dots and line segments, vertices and edges, that's a graph. Example 1 says, draw a graph that shows these seating arrangements. So you've got this chart. And what I'm going to do is I'm going to draw a dot for each of the people. Here's Andy and Billy. And it doesn't really matter where you put them. I'm just going to kind of spread them out into like a circle. There's Karen with a C. Dave. Aaron. Felicia. Okay. So what we're trying to draw a picture of, what this graph is going to be, is just a picture of the relationships in this problem, or specifically who each person sat with. It says that Andy didn't sit with anybody. Andy sat with no one. So I'm not going to connect him to anyone. I'm going to go straight to Billy. Billy sat with Dave. So I'm going to attempt to connect those two. There we go. Billy sat with Aaron and Felicia. So these edges show connections. Karen sat with Dave and Aaron. Dave sat with Billy, which I've already got that one, and Karen, I've already got that one, and Felicia. Aaron sat with Billy, I got it, and Karen, I got it. Felicia sat with Billy and Dave, I've got both of those. So really that's it. That's your graph. And what we're going to use graphs for is just to, we're going to use them to solve problems, but being able to draw a picture of a situation is really going to help at some point later. A simple graph has no multiple edges between vertices and no loops. Okay, so multiple edges, like right here, that's 3 different edges that go between the same vertices. Okay, that's multiple edges. So this one's not simple. This one right here, if you notice, there's a vertex, and then this edge loops around to itself. That's a loop. So this one is not simple. The only one of these 3 that's simple is the first one. A simple graph has no multiple edges and no loops. The number of edges joined to a vertex is called the degree. And the easy way to see degree, look at number 2, find the degree of each vertex, is just think about how many lines is coming out of each dot. So if you look at vertex A, there are 1, 2, 3, 4 edges coming out. So that degree is 4. And B has a degree of 3 because there are 3 edges coming out. C is 2, D is 0, E is 1, and F is 2. So we can find the degree of each vertex, and that's going to help us solve a lot of problems at some point. Isomorphic graphs. This is a hard one, okay? Graphs with the same number of vertices and edges and the exact same relationships between vertices and edges. So isomorphic pretty much means they're the same. And so if you think about it, don't think about a graph as being rigid, okay? Think about a graph as being like those dots are like magnets on a board connected by rubber bands. And I can move the stuff all the way around, but they're all they're connected in a certain way, in a specific way that's not going to change. Okay, so this graph that I just drew, I could draw the exact same thing. Those two things are the exact same picture. I've got 4 dots connected by 3 edges. Those connections are exactly the same. If you visualize moving the magnets around with the rubber bands, the lines don't even have to be straight. Okay, I could draw something like this. And that would be the same exact thing. I've still got 4 dots connected by 3 edges. It's the same thing. So don't think about it as having to be rigid or stuck in one place. You can move it. And that's what I'm talking about when I'm talking about isomorphic graphs. Connected graph. If one can move along the edges from one vertex to any other vertex. Like this. Okay, if I could go from here and just kind of travel along a path and get to any other vertex, that's connected. Connected graphs have one component. Disconnected graphs have more than one component. Number 3 says label figure 2 so that it is isomorphic to figure 1. Okay, so what I want to do is kind of pick a vertex to look at first, this one, and I'm gonna start with this one and call it A prime. Okay, I'll just call that A prime. It makes me look at the A. It's the same thing as A. It's just I'm not gonna label it A. Okay, if you just kind of try to travel in a path, you would know that A travels to point D, and so one thing we can do is kind of look at this picture, figure 2. That means this must be D prime. Okay. In order for this to, to see that it's an isomorphic graph, just travel the same path. From D, I go to B, so that must make this point B prime. And from B, I go to C, that means this. I'm just traveling around a path, must be C prime. And then from C, you go back to A. C prime goes back to A prime. Those are the exact same things. And you can tell when you labeled it. Okay, so again, don't think of your graph as being stuck in one spot. Think about those dots as being magnets on a board and the edges being rubber bands, and you can kind of move stuff around. All right. Number 4, is this graph connected or disconnected? Well, if I'm traveling on this path, I have to go from dot to dot. I can't get from any of those 3 red dots to this blue dot or any of these blue dots right here. Okay? I can't get from a black dot to a red dot or from a blue dot to a black dot. That graph is not connected. In fact, I could take that blue one and I could move that blue thing over here and it'd be exactly the same thing. Okay? It's not connected. And I see 3 components. Specifically a red one, a blue one, and a black one.